Okay, today we are going to talk about lighting calculations and doing them by hand, and really what goes into how to do lighting calcs. So first we want to know, lumens at the workplane, which means we need to know a couple things. So lumens at the workplane, we need to know the initial lumens. So you'll find these on a cut sheet. So whatever the initial lumens are, times the light loss factor, which is known as LLF. And then we need to know the coefficient of utilization. So what are these things? So initial lumens, we're going to find that from a cut sheet, fixture sheet. The light loss factor, so light loss factor equals dirt depreciation times the ballast factor, we're just going to say BF, times lamp lumen depreciation. What this meant, so dirt depreciation is like any dirt buildup that gets on the lens. You saw this a lot more in fluorescence as you had basically open lamps, and they needed that openness really for airflow around the fixture so it didn't overheat and burn up. So dirt depreciation, since everything is sealed, really this is like a 0.98 ballast factor. So you lost some lumen output from say you had a lamp and you had no ballast on it. In fluorescence, you could get a ballast factor of 1, but since you had a ballast, it didn't drive the full amount of current to it, so you got something like 0.85. In LEDs, really you get 1, and this is for LED. It's like 0.85 for fluorescent. So we're not going to worry about this. So really for LED, it's 1 times lamp lumen depreciation, which this you're really going to like the half-life of the fixture, and really you look at like 0.87, and that's really to compare to effectively what you would look at for like a T5 or a T8. So our LLF equals 0.85. And that's going to be typical for any LED, is 0.85. Now our coefficient of utilization. So in coefficient of utilization, this really comes from, so our coefficient of utilization, you need to know the IES tables. So like the IES file, which is determinant of, depending on your room, what that fixture actually looks like. So there's a few things that go into this. The thing that you'll need to calculate before we go to this table, is you'll need to calculate the room cavity ratio. So that's room cavity ratio. And a room cavity ratio, so RCR, there's actually 2 ways to do this. One is for like a simple typical room, and another is for like an odd geometry. I'm going to show the odd geometry because it'll always work and you won't have to remember, do I use this or that? So this is what we're going to use. So it's going to be 2.5, which is a constant, times, so we want to know the height of the fixture, minus the basically workplane height. And we'll go through an example here at the end. And then times the perimeter of room. And you're going to divide that by the area of the room. So a simple example, okay, let's say we've got a 20 by 10 And then if we look at it in section, got our ceiling with our fixture in it. And then we've got a table. Here's a chair. So from here to here, let's say this is 10 feet. And then from here to here is 2.5 feet. So if we look at the height of the fixture minus the height of the work plane, so our ceiling height, so it's really 2.5 times our ceiling height, which is 10, minus 2.5 times the perimeter. So perimeter is 20 plus 20 plus 10 plus 10, right? 20, 20, 10, 10. And then divide that all by 20 times 10. So we're looking at 2.5 times 7.5 times 20, 40, 60, all over 200. That's 5.625. So now we have our room cavity ratio. You'll go over to a coefficient of utilization table. So I've shorthanded one here. And what you need to know on this is really these things first. So you'll need to know the floor reflectance. Typically it's 20, and then the wall reflectance, or the ceiling reflectance, and then the wall reflectance. So typically it's 80, 50, 20, so 80 on the ceiling, 58 on the wall, 20 on the floor. And within basically any IS sheet, you're always going to see this. This will always be there. You have choices for some of these others. Some will be 80, some will be 70, some will be 50, and then 70, 50, 30 on the walls. So the floor is actually first in how you read the sheet, and then the ceiling, and then the wall. So there'll be basically a big header. It'll just say 20%. It'll have PF for coefficient floor, and then it'll have PC, and it'll have like 80, 70, 50, and then under it'll be PW, and then there'll be 70, 50, 30, and then there'll be a bunch of numbers under it. And then that'll be for each of these. So what I've done is taken from a fixture schedule, just a simple coefficient of utilization, all the numbers. So what does this mean? This means that, so if we go back over here, we can look at our coefficient, our room cavity ratio is 5.65. So right here, so 5.6. So we're going to be between 61 and 55. 61, 55, right? And then we'll extrapolate that 5.625 between the two. You can look at how to do extrapolations. We're going to extrapolate the data from two linear points. So y of x equals y1 plus x minus x1 over x2 minus x1 times y2 minus y1. All right, so big long fancy formula. So what does this mean? So really when we look at this, we have effectively x's and y's. So our x equals 5.625. Our and then if we look at the other points, so we have 5, 61, and then 6, 55. So if you remember from math class a long time ago, or algebra, so we're really looking at y of 5.625, which is just a fancy way of saying we're going to put 5.625 in for this x, and then so this is our x1, y1, x2, y2. So then we look at y1, so that's 61, plus x, so 5.625, minus x1, 5, over x2, which is 6, minus 5, and then times, so this all gets multiplied, y2, which is 55, minus 61. So let's simplify this a little bit. So now we have effectively, let's make this a little easier for everybody. So we've got 61 plus 0.625 over 1, which is really 0.625 times negative 6, 61 plus 3.75, which is actually minus 3.75 equals 57.25. So this is our coefficient of utilization. Obviously, it's a lot easier when they match up to a given number, but that is our coefficient of utilization. So now that we have that, if we come back, our formula was initial lumens times light loss factor times our coefficient of utilization. So let's work this out. So really the lumens at Workplane now equals, so our initial, and I went with a 4,000 lumen fixture, times light loss factor, which is 0.85, times our coefficient of utilization, 57.25. That's coefficient of utilization. All right, so you're seeing a little herky-jerky here because I didn't have a calculator and had to use my phone. So video paused, but now we're back. So initial lumens times light loss factor times the coefficient of utilization. Remember, this is a coefficient, so it's in a percentage. So really remember to divide this by 100. So if we multiply these all up, 1946 is really our lumens at the work plane from this one fixture. Again, so the bigger your cavity is, so the bigger the height between the fixture and the work plane, the lower, so the greater this number is. So as this goes up, your coefficient of utilization actually goes down. So just remember that. That's why you need more fixtures in a bigger space than in a smaller space. So 1946 is our lumen count, and if we take this, so if we put one fixture, this one fixture in our 10 by 20 room, which is 200 square feet, so we take 1946.5 over 200 equals 9.73 foot candles, which is pretty low. So, and then you add these up, so however many fixtures you end up needing to reach whatever foot candle level that you're trying to get at, or you increase the lumen count. So lumens go up, or fixture count goes up. So that is really how you find the lumens of the work plane for a given room.